To get better rates on mortgages, loans, and credit cards, you don't need to know the friend of a friend of the second cousin of a dog walker who went to school with the adopted son of a reflexologist who's currently plant sitting for the stepsister of a social media influencer that lives next door to some guy who works in finance. You just need a little help from Experian to improve your credit score. Download the Experian app and check your credit score and report for free today.
Hello and welcome. This is the Michelle Hussein Show. I'm Michelle Hussein. I speak with people like Elon Musk.
I think I've done enough.
And Shonda Rhimes.
That's so cute.
This will be a place where every weekend you can count on one essential conversation to help make sense of the world. So please join me, listen and subscribe to the Michelle Hussein Show from Bloomberg Weekend, wherever you get your podcasts.
You certainly ask interesting questions.
Well, that's much better. Good evening and welcome everybody. My name's Obi-Wan Pez. This is N Simplex Pachinko, and we are working on some math stuff tonight from Cracking the GRE Math Subject Test by Princeton Review. This is the second edition of this book. Not much has changed, but this was the book that I used in 2004. So, basic idea is that we've been going over individual topics and ideas and then using this as a source to get practice problems and that kind of thing. So, I believe last time we worked on finding the area between two curves, and we did just simple like square root and quadratic function. And we did it in both directions, or at least talked about how to do it in both directions. If we do real quick, just want to look at calculus. In order to get a more interesting type problem. so why don't we take take one of each or something like that. Grab a quick screen grab there. And then we can also look at this from the... That's not what I wanted. Screenshots. Every time. Still makes me jump. Hey Zach, how's it going? Okay, so what I'm going to do, I'm actually going to modify this a little bit and say we're not just going to do x from negative pi to positive pi. I actually want to take it as what is the, find the first instance of these particular functions being coincident and try to find the obvious area between the curves. We can also look at what happens when we do go from negative pi to pi, because they cross over eventually at some point. So just want to look at that afterward. So first thing we do, we can look at it like this. We have a sine function, which is going to come up like this. Really should do this a little more carefully. So Zach, you remember when I said here, here. So you have the cosine function. Looks like that-ish. And as always, if you mess up your graph, just make the point bigger, and then nobody will know. Right, so we have pi over 2 here, we got pi over 4 here, and 3 pi over 4 here. Okay, so this is y equals cosine of x, and then also we want, let's do green, the sine function, which has zeros at 0 and pi, and then we have pi over 2. It has a value of 1, pi over 4, it also has a value of root 2 over 2, which is approximately 0.707. And then also at 3 pi over 4, it has the same value. And from here, it can go like that, and it can go like that. Okay, so by first instance here, what I really meant was now we've got this area here. So that is the area we're trying to find. We're going to do it both from the X and the Y perspective, and you should be able to see why one of them is a little bit easier than the other in this particular case. You'll never believe it, Zach. Found out that one of my wisdom teeth was cracked today. Ran my tongue over it, and it had this nice little crack in it. I'm like, oh, that's not good. Called the dentist for an emergency appointment. They were like, great, see you Friday. Damn it. Okay, so for this, the basic idea first, if we're going to do this from the x-axis perspective, to say that x is our independent variable, is we're going to take this and we're going to say, in order to do the find the area between two curves, remember what we're doing here is we're saying that we want to take the integral of f of x minus g of x dx, where f of x is going to be the higher one and g of x is going to be the lower one, or the higher and lower valued functions for that particular area. So what we found here is that we're going to be taking the integral as we go in the x direction from 0 to pi over 4, where they intersect, of the upper function, which is cosine of x, minus the lower function, which is sine of x, dx. All right, and that's it. Right, so for the x independent variable, this one works very nicely. I do recommend for my students that they put in the rectangle that they're attempting to integrate. So here we have our f of x for the rectangle. Here we have our g of x, and again the height of the rectangle itself is going to be f of x minus g of x, whereas the width is going to be dx. So if we're trying to find the area of this particular curve, or the area between these two particular curves, then we have the height of every single rectangle is going to be f of x minus g of x. The width of every single rectangle is going to be dx when we start talking about an infinite number of rectangles. If we wanted to, we could even go further and say, hey, remember how integrals actually work? We're trying to do f of x minus g of x as the height times whatever delta x we might have. So again, there might be a number of different delta x's, and all of these x sub I values are also going to be individually selected. We're trying to sum them all up as I goes from 1 to n, and then, because we're doing an integration, the integration really works because we say we want to take the limit as n goes to infinity. So we get an infinite number of rectangles, and then it will account for every single little bit, and it won't account for any extra bits. Unlike our Riemann sums, which is just this first bit, or the second bit here. Right, we take our Riemann sum and we say, okay, now we're going to take a limit as it goes off to infinity. Well, not quite that. Let's go like this. So we take the Riemann sum, we take the limit, and that's behind my head. And when we take them together, that's when we get the integral. Right, so for this, we're saying that we want the integral as x goes from 0 to pi over 4 of cosine of x minus sine of x dx. And then when we do that, that's going to get us, again, this whole area in here for all of that. So, integral, or rather the antiderivative of cosine, is a sine. We don't have any other arguments that are going to confound this or transform it or anything like that, so it's just sine of x. And then minus. Now the antiderivative of a negative sine of x is a positive cosine of x. Right, so if we take the derivative of the positive cosine, we get a negative sine. Again, no arguments to transform this at all. And then this is going to be evaluated as x goes from 0 to pi over 4. So, what are we going to get? Well, this is the area. So area is going to be equal to the sine of pi over 4. And we could do it pretty much any way we want here. Minus sine of 0, right, plus cosine of pi over 4, minus, nope, cosine at 0. So the area is going to be the sine of pi over 4 is root 2 over 2, and there are 2 of them. And then we get a minus cosine of 0 is 1. The sine of 0 is 0, so that's gone. So our area here is root 2 minus 1. So instead of a 1.414, this is going to be a 0.414. Right, there are more digits, but we're just not dealing with that right now. So, what do we do if we want to do this from the y perspective? So if we're going the other direction instead, that'll be okay. We'll just, oh, gross. Alright, move this down here. We go with y being independent. I'm going to take out all this stuff for now, just because I want to be able to see it. This is not going to work, and I need to stop using my mouse, otherwise I'm going to erase more than I wanted to, like I already did.
reflexologist who's currently plant sitting
Okay.
for the social media influencer that lives
So in this case,
on
y is going to be the independent variable.
finance.
We've got this.
Just need a little help from Experian to improve
Ew.
your credit score. Download the Experian app and check your credit score
There
and
we go.
report for free today.
So, y is the independent variable in this case. And so what we're going to do is we're going to go this way with our rectangles. Now, this creates a little bit of a problem in that there is a cusp here. We're going to have our horizontal rectangle grow and grow and grow and as we're moving down. As we're moving down, it's going to grow and grow and grow and grow and grow, and then it's going to freeze, and it's going to immediately start doing something else and start shrinking again. That doesn't really work so well to lend itself to like a single nice function. So in this particular case, if we look at what's high and what's low, we notice that the function that we're using for each of these as the high-valued function, the top function, are f's that we had in the other one. Well, it's going to create a problem because now we have two different f's, and the g function, the lower valued function, is just the y-axis. So that's x equals 0. So here we're bounded by y equals cosine of x and y-axis. So x equals 0. Well, now these are two different variables in terms of independent and dependent variables, technically. And this is when y goes from 1 on the top end to root 2 over 2 on the low end. Right? And then we're bounded by y equals sine of x and the y-axis, which again is x equals 0. Okay, so first of all, we got to get everything in terms of x equals rather than y equals. And that's when y goes from 0 up to root 2 over 2. So we're going to have two different integrals. And again, we could break this down and go with the Riemann sums up above, but we'll let that go. Okay, so the y equals cosine of x is going to be x equals inverse cosine of y. And then y equals sine of x is going to be x equals inverse sine of y. You're going to yell at me. Hashtag not sponsored. Yeah, I have a little teeny tiny bit of moonshine left, so I was like, it's not gonna. Roughly speaking, right, I could dirty a glass, or I could just drink the rest of what's here, so. Okay. So with this, then we're going to create two separate integrals. The first integral is going to be the integral from y equals, well, let's do it numerical order. So 0 to root 2 over 2 of sine inverse of y dy. Okay, plus separate integral going from y equals root 2 over 2 to 1 of cosine inverse of y dy. And now this covers both of our y sections, going from 0 to root 2 over 2 and root 2 over 2 to 1. Okay, next question. What is the integral or antiderivative of inverse sine? Right. It is possible. I just don't know what it is offhand because I'm terrible at this stuff. But anyway. Ah, right. So we could do it via integration by parts. So u is going to be equal to sine inverse of y, and dv is going to be equal to dy. Therefore, du is going to be equal to, this is one of the ones that I always get wrong, 1 over so 1 over square root, which is rather ironic given. Right. It's like dy over 1 minus y squared. That doesn't have the bit that comes out. Arc sine. Yep, there we go. Right. And then v is just going to be y. So, integral of u dv is equal to uv minus integral v du. Just as a reminder in case anybody forgot. Right, so here we're going to go with uv, which is y inverse sine of y, evaluated from 0 to pi over 2. Nope, root 2 over 2. Minus integral of v du, which is now going to be y dy over square root 1 minus y squared. Now, interestingly enough, right, this can also be done. This square root, or this integral can be done because we have a y out front and a y squared on the bottom. This is now going to just get us a regular u substitution. So, with a regular u substitution, let's see. Inverse sine of 2 over 2 minus 0, because here we have a 0 up front and also an inverse sine of 0, which is 0. So, both of them are 0. In the second case, we have the negative, right? Negative y dy is du, or the du. If we let u be 1 minus y squared, then du is going to be negative 2 y dy. So we need a 2 here, which means that we also need a 1/2 on the outside. In order to get the nice antiderivative. It's not like it's super necessary, it's just nicer to work with it that way.
You certainly ask interesting questions.
And again, the negative is going to come inside and be part of the du. So this means that we get a plus plus 1/2 here. Okay, well, I tried. The exponent on this is a negative 1/2, which then increases to a 1/2. We don't actually have that, so this is going to be a 1 over 1/2. Which means all that's going away. Multiplied by the square root of 1 minus y squared on top. Evaluated from 0 to root 2 over 2. Okay. Okay, good. This is root 2 over 2 multiplied by the sine inverse of root 2 over 2 is pi over 4. Plus, here, this is going to be the square root of 1 minus root 2 over 2 squared is going to be 2 over 4, or 1/2. Minus square root of 1 minus 0. So just 1. So this is going to be root 2 times pi all over 8 plus square root of 1/2, which is still root 2 over 2, minus 1. Oh, that's only one of them. Right. That's important. Right, so this is going to be plus what we get from the other one. So this is going to be u is equal to inverse cosine of y du is equal to, this is going to be the negative dy over square root 1 minus y squared. Dv is equal to dy, and therefore, no, v is just equal to y. Same deal. Okay, so then we do the exact same thing with the different limits of integration. So this is going to end up being uv, so y cosine inverse of y, evaluated from root 2 over 2 to 1. excuse me, minus integral from root 2 over 2 to 1 of, here we get v du, so this is a negative y dy over square root of 1 minus y squared. Same integral as before, but this one already has a negative inside, so now we just need the 2 and a 1/2. And actually that 1/2, right, can be used for the integral. For the exponent term that's coming up. So here this is going to be 1 times cosine inverse of 1 which the cosine inverse of 1 is 0. If anybody does have any questions, let me know. You know, as much as I use this framework for building, nope, this is not it, for cracking the GRE, my priority is going to be to help anybody who wants it. So if anybody has any questions, let me know. Right, so here we have this negative here, which is going to be used as part of du. The 1 minus y squared is our u, and then therefore negative 2y dy, which is all in the numerator, is going to be the du. And then the 1/2 that's out front is going to be brought in as part of the square root transferring to the top, and needing that, you know, 1/2 term raised to the negative 1/2 power, right? So all of that together. This is part of the antiderivative. It is just going to come out with a negative square root of 1 minus y squared. And that's evaluated from root 2 over 2 to 1. Which is minus the 1 is going to get us a 0, and then plus I just snubbed the root 2 over 2 there for no reason whatsoever. Let's move all this over. No, hang on. No reason, honestly. Minus, right? This is the root 2 over 2 times cosine inverse of root 2 over 2. Okay, and that's a 0 for the first one. The second one is a negative root 2 over 2 times the cosine inverse of root 2 over 2 is pi over 4. So, not really surprising there. That is identical to the first term. So we end up with a negative root 2 pi over 8. So all this and all that are going to divide out. They're gone. Then, right, we get a 0 for plugging in 1 inside the square root. Then, minus the negative, which is now a positive, square root of 1 minus root 2 over 2 squared is again 2 over 4, which is 1/2. Okay, which is square root plus plus square root of 1/2. Right, I didn't need a giant. Don't know why I did that, honestly. That's fine. And, right, root 2 over 2 plus root 2 over 2 is equal to root 2 minus 1 that we already had from the other bit. So the answer here, the area is root 2 minus 1. So we get the same answer. This was a lot more involved. We needed to use the integrals of inverse trig functions, which turned out you can solve, but you need integration by parts twice using two different integrals because we are turned sideways where there ends up being a cusp. So in this particular case, it ends up being so much easier to stick with using our x as our independent variable. Now there are going to be plenty of examples where the opposite is true, that you're going to have the boundary between two functions is going to have a cusp in x, but not in y. And when that happens, great, you know what to do, flip it on its side, use each of the functions as the higher valued function and the lower valued function, and just say higher minus lower is going to get you that full horizontal distance. All right. So and again, if anybody has any questions, let me know. I can work on that instead or in addition. I mean, functions in y are pretty obvious, but so in the case of number 21, right, x equals 2y and x equals y cubed minus y. So in order to get this, we want to look at first what is the graph going to look like for this. So x equals 2y, every x value is twice whatever the y value is, so it's going to start at 0, 0, and then the x values are going to grow twice as much as the y values. So it's going to get us a function like this. This is what we would know it as y equals 1/2 x. right? And then this one here, x equals y cubed minus y is a cubic function, but it's in the y direction, so it's going to end up making an S sort of shape this way. It is not a function in x. It is, however, a function in y. So here we could look at this and say, what are the zeros? Right? Y parentheses y squared minus 1 is y times y minus 1, y plus 1. So zeros are going to be, if this is equal to 0, y is equal to negative 1, 0, positive 1, as the three zeros to this particular function in y. So if we go down to up to 1 and down to negative 1, we're also going to get points there. All right. Now what? Right, if we went to 2, for example, right, 2 cubed is going to be 8 minus 2 is going to be 6. So if we went to a yeah. Y value of 2 is going to get us out to here. So this is growing very quickly. Whoops. Okay, and then that's going to keep going that way. So this is x equals y cubed minus y. And we're not really going to be able to solve this for x, or sorry, to solve this for y to get a nice version of it. Like, oh, it's partly cube root. Not really. Pro tip, don't inhale tea. Okay, so this is going to come down here. It's going to make a bump. It's going to come up here. It's going to make a bump. It's going to come down there, and it's going to go that way. So when this is saying, like, find the area between the curves, right, how do we do that? Since I'm looking for the first instance of it to occur, I'm just going to look right next to the origin and see, like, oh, look, there's an enclosed area. Let's use that. So the best way to do this one is going to be to go sideways, because we can use our x equals 2y as our top function, the higher valued function, and then the x equals y cubed minus y as the lower valued function. And when we do that, we only have to go from y equals 0 to y equals whatever the intersection point is. And this is easy enough to figure out, or at least easy enough to start the calculation. We know that x is equal to both 2y and also y cubed minus y. So this means that 0 is equal to y cubed minus 3y. And so therefore 0 is equal to y parentheses y squared minus 3. And wouldn't you know, there are values that make y squared equal to 3. Right, so y equals 0. Or plus or minus the square root of 3. So since we are only going with the top one at the moment, that is going to be the positive square root of 3. So we want the integral between 0 and root 3 such that, or of the difference of the functions, 2y minus y cubed, parentheses, y cubed minus y dy. Okay, so from 0 to root 3, we have here 2y minus negative y is going to be plus, so we get 3y, and then minus y cubed dy. So when we do this, now we've got, taking the integral of 3y, we need a 2 in order to increase the exponent to y squared. So we didn't have 1, so we can either, again, split from a form of 1 or just say we need a 2, we don't have a 2, therefore we need to divide by 2. So 3 over 2 y squared minus, and again, same here. We need, in order to go up 1, we need a 4. We don't have a 4 out front, so it's going to make a 1/4 y to the 4th. Evaluated from 0 to root 3. Zeros are going to be 0. So we can essentially say that this is just not going to count. We're just going to get a plus 0 at the end. And then to get the root 3, we're going to have 3 halves times root 3 squared is just going to be 3 minus 1/4 times root 3 to the 4th power is going to be root 3 squared squared. So root 3 squared is 3. Squared again is 9. Okay, and if anybody has been studying quadratics and they want to know where their vertex is and things like that, this should look very familiar. Here we have 9 halves minus 9 fourths. So this is going to end up being 9 fourths. All right, area for all this stuff. Area is going to be 9 fourths. It is not going to be particularly nice if we try to do this in the x as the x. Yep. If we try to do this as with x as the independent variable, we're going to have a bit of a problem with this. So the first thing that would need to be done is we would need to figure out what this difference of functions is going to be here, because we've essentially got a positive and a negative branch of the same stuff. So I don't even know how to deal with that, really. And then also if we went with the other one here, right, this would go up until 0. And then you have a new branch above 0 that has the cubic function as its top and the linear function as its bottom. So that one is easy enough to deal with for the bottom. But the problem is going to be then we need an explicit form for the numerator, for the top function, which is currently in terms of y. So I don't think I actually know how to solve for that particular equation. So seems that in this particular case, right, being able to do the horizontal the horizontal rectangle. So have your functions in terms of y. In this case, they were given, and it makes it just that much easier. Okay. I think that's probably good for area between two curves. So let's actually, right? Let's look at polar coordinates. So standard Cartesian also known as rectangular coordinates. Have points that are your standard x and y. So if we just pick a point in space, we count out in the x direction, we count up in the y direction. These are orthogonal to each other. So they meet at right angles. Now none of this has to be that way. It could very well be that we have some sort of skew coordinate system like this, and it could be that, you know, we having a thing out here, again, we count this way for x and then go this way for y. This is perfectly possible, but we don't typically do it. So when you get up to, like, you know, the level of talking about tensor calculus and stuff like that, then there's all sorts of coordinate systems you can use and start varying those coordinate systems to suit whatever needs you have. For us, most of the time, rectangular Cartesian coordinates are perfectly fine. They work, you know, 99.9% of the time. They're much easier for most people to use because that's what they've been exposed to. There are, however, many different types of coordinates we could use, one of which is polar coordinates. So when we do polar coordinates, what we're doing really is we're looking at the globe as if from above. So if you look at a globe from above, you'll see concentric rings known as latitude, and then rays that come off of the origin point, which we which we will call longitude. So having this latitude and longitude, we can then also give our coordinates as a piece of information with 2 bits of information, which tell us 2 particular things. One is at what angle at what angle are we talking for any particular point. So for this one, right, this is this angle right here. You can draw a ray which goes out to that point. And that is our angle theta. The other piece of information is then, if you're talking like a compass course, for example, right? What bearing is it to the next marker, and how far is it to the next marker? So what would be the radius of the circle that gets us out to that point? So r comma theta is going to be the other important piece of information in order to get us to this particular point in polar coordinates. We could still do it in Cartesian, right? We still get x and y as our two orthogonal distances from the origin. It's still in the exact same place. It's just now we have a different way of referring to it. So r comma theta. This does mean that this particular one with my terrible drawing is going to be 1, 2, 3, 4. So let's say this is going to be at 3.8 comma 3 pi over 7. Right, something like that. Actually, that's wrong. Pi over 7.
Sean has had some good ideas over the years.
No, because that would be below pi over 6. Alright.
Sean designed some social posts to promote his friends.
Somewhere between pi over 6 and pi over 4. Oh, okay, yeah. How about pi over 5?
Next thing he knows, someone bought the craft, including
Right, so 3.8 comma pi over 5 will get us this particular point, r comma theta. That's that green dot on there. Okay, so how can we then go back and forth between polar and Cartesian coordinates? Well, we already have equations for this. We know that x values are found using, in fact, let's go the other way. The cosine of theta is defined as x over r, the radius, and the sine of theta is defined as y over the radius. All right, gonna have a 3-minute ad break. So we'll see you all in 3 minutes. Thank you for coming. And if you have any questions, let me know. We'll answer something. And yeah, we'll be back. Welcome back, everybody. I was doing Tai Chi for almost 2 hours today. Arms turned a little bit into jelly. Legs, too. The instructor. My instructor ended up discontinuing our Eskrima class, unfortunately, just because there's only 3 of us, which doesn't make sense financially to keep it going. But he's doing Tai Chi lessons essentially like 3 times a week, so I'm showing up to at least 2 of them. At least that's the idea. Sorry, these are my son's socks. He hasn't been in the house for like 3 days. That's something else they do over here in England. The kids go on residential trips, like a lot. They have one a year that they take to some sort of like outdoor education place. This one is the big one. So he's in year 5. And they, which is 4th grade. So that area. And the kids go and they go to this outdoor education place. They do all sorts of crazy stuff. They go caving, they go rock climbing, they go all sorts. And they're gone the entire week. So we dropped them off on Monday, and we won't see them again until Friday. Like, nuts. So things have been quieter around here. It's weird. But he'll be next year. The year 6s go on a trip to Stratford-upon-Avon and go and check out Shakespeare's house and like all sorts of other stuff. So it's pretty cool. Hey, Famished. How's it going? Kids gotta clean up the toys. I know. And like, this is clean. The fact that I have a space enough to like walk around in is just amazing. In all seriousness though, right? Here's the other thing, is like, this is all kind of in like piles, but they're all just brightly colored. So you'd barely be able to see any of this if... Just kick this back over here. See, can't even see it anymore. Room looks so much bigger already. Already been warming up. What am I doing? So yeah, I went and at least they actually use it. Yeah, that's true. And like these are the paints for who's it? Yeah, these are all stuffed animals. Those are all paints for my minis. So like that's mine. Let's see. Yeah, like I said, we kind of already did warm up earlier. um, somewhat with my instructor. He also was showing me. I got to bring down my bow staff from upstairs. He was showing me an exercise that, like, he used to have to do it in Malaysia when he was. He's a Yorkshireman, but he was like studying Tai Chi for 15 years, and then they decided, hey, you should come to Malaysia and study with like the actual master. And so he spent like, I don't remember what he said, probably a year or two studying under the master, and then came back and was like, just working with all the guys around Yorkshire, and he was just realizing like how much he really wanted to do Tai Chi. We did learn a couple of interesting things today with Tai Chi. Not that I can do that with an eskrima stick, but it's fine. We'll just talk. There was an exercise he used to have to do in Malaysia, and it's like you take a 6-foot staff, you've got it probably about here and here on the back end, and you hold it up to about your chest level, and then you are standing feet together, you step out, and as your body weight sinks, you have to throw the whole thing down until it goes here, and then you pick it back up, and then you throw it back down, you pick it back up, and the end, if you've got like a nice supple piece of wood, this is not, it's just small, but like the end will just go, and he said if you can transfer like your energy from throwing this thing down into the stick, into the stick, and it kind of gets that like sharp wobble to it, then you know you're doing something right. Working on a text style survival game for Twitch. Nice. As in for people to play on stream, or as in for you to do on stream? I don't think you stream, do you? You do something. Okay. People to play while you do work. Oh, okay. Yeah. Neat. Let's see. That's this. So this is a... come on. I remember the name a couple weeks ago. Why am I not remembering it now? Fan block. Also called... Well, shoot. Abanico. There we go. Abanico is the fan block, and then the follow-up comma sort of shape to it. Kadak. If you basically, if you get into a position that you can keep doing something and then reversing it, right? You get the muscle memory. All right, Abanico, Catholic. Strike, or not even a strike, you just come from here. Go to the Abanico, Catholic, strike. Yeah, so I'm feeling a little bit upset. I mean, not upset, but a little bit. It's unfortunate that he had to discontinue Eskrima, but I'm going to be learning a lot of Tai Chi from this guy over the next year and a half. So, provided everything goes well, yeah, I'm going to be cross-training in Tai Chi, in addition to Tang Soo Do. So I will. That's still going to be like my primary martial art. And I mean, once I go back home to Maryland, I'm going to probably rejoin the same org and see if I can't get my black belt in the next, well, a year or two, with us getting back there. Leaning towards co-working. Nice. That kind of reminds me. Do we have a... There does not appear to be a martial arts category. It's interesting. Huh. Plenty of karate, but not... They're all games. It's too bad. Yeah, it would probably be fitness or working out. And it's a reasonable category. Oh. Here's the idiot over here who only just saw your rebrand. Did you just change your name like yesterday? The last I knew it was Famished Edits, but I was also over there, so I mean, it was clearly shorter. 2 days, yeah, okay. It was clearly shorter than Famished Edits, but yeah, just it didn't register. It was just like, yeah, I was looking at the first apparently 5 letters. They were the same. It's fine. Now you're stuck with it for like a year, right? Oh, okay. Within 60 days. I had an unfortunate incident this morning in which I ran my tongue over one of my teeth and noticed that there was a crack in it, and I was like, no. This is like the first tooth that has had any actual problems other than just, cavities and stuff like that. And I was hoping that it was just like a piece of oatmeal, like one of the hulls. I was hoping it was just a hull that, like, it's stuck in back of my tooth and I just can't get it out and it feels weird. And then I like just bit down like that, and like a shard of tooth was then like compressed and then pushed down out, and I went, nope, we're done. So I got home, I got a pick, and I just kind of like, let's just hope it's not what I think it is. I went like that, just like a little hook and tug, and like a piece of tooth came out, and I was like, all right. Well, that one's done. So, I have to go to the dentist on Friday afternoon and have my top left rear, well, I mean, obviously it's in the rear, top left wisdom tooth finally taken out. I'll send it back to my dentist in New Hampshire and be like, here, you can have it. He was weird. He was always just like from the time I was about 16 and they started getting close to the surface, close to erupting. He was like, we can dig those out for you. I'm like, no. You took out 4 of my permanent teeth up here in order to get everything moved forward so I'd have space for my wisdom teeth. Why would I want you to dig them out? And it was like, I was 21 and still on my parents' insurance. And he was like, I mean, last chance. And I'm like, no. So now I'm just like doing saltwater rinses every time I eat something, and eating with only one side of my mouth. Here's the worst part. None of this hurts. Which tells you that there was something really wrong with it. So, seems that the tooth essentially is/was dead, and like it's not even registering anything right now, but we don't want to tempt fate or cause any infections or anything like that. So saltwater rinses it is.
Nothing beats family time. Quality time spent with catching up on your debt. Business admin cutting into family time. Sounds like you need to supercharge your bookkeeping with Xero. With automated bank feeds, smart reconciliation, and online payments, your business can do its thing while you do yours. Supercharge your business and get back to what really matters. Tap the banner to try Xero free.
All right, so if we want to move stuff around, between polar and rectangular coordinates, these are the equations we're going to use. So x is equal to r cosine theta, and y is equal to r sine theta. They're integral to this entire process. Mm-hmm. that was a goal for a while. It was like, get all these people from anywhere, study in the U.S., and then go back home, and then they've been trained in, like, American Medical Association, American Dental Association, like, to that level. Because, I mean, the AMA and the ADA, at the very least, used to be the absolute, like, pinnacle of world health. Don't know how it's going anymore, but, yeah. Yeah, I mean, we always just make sure that we've got dental. My spouse was just about to cancel it, because, like, for the last year and a half, we could just get NHS cleanings. We're on the National Health Service in Britain, so we can get NHS cleanings through the practice that we go to, and they're, free. Or our copay is like £10. And if we went through, I mean, we can't do American insurance, but if we were, or no, we can use the governmental insurance that works with NHS. So if we were to do that, then cleanings would end up being like a $20 or $30 copay, so still more, but nonetheless. And then tooth extraction is like, she said, why don't we look at the bill when it comes in and then decide whether it was whether it's worth sending it back for reimbursement, because, like, we can send stuff to the insurance company for reimbursement after the fact, or we could just pay the NHS for whatever they request. But I don't think we can do reimbursement if it's like less than $400 or something like that. I don't know. Either way, this thing has to come out, and it doesn't hurt, so that's potentially bad. We'll be doing saltwater rinses for the next month. All right. So, polar coordinates from and to rectangular coordinates. Again, here we're looking at these functions here. Well, these transference equations, which are going to allow us to go from rectangular to polar or vice versa. All right, if we want to, it would actually be easier to make these equations go from polar to rectangular, because what we have is that we have our r and theta on one side of the equation, and then x and y are already solved for. So naturally, if we want to go to rectangular, this is easier. If we want to go rectangular to polar, then what we really want is some way to get r equals and theta equals from using x and y. So one equation that's real easy is we know that if we go with what's on this graph, we have a right triangle, and its sides are x, y, and r. And so here we have x squared plus y squared equals r squared. Therefore, r is equal to the square root of x squared plus y squared. This is only going to be the positive square root because this is only going to be the positive square root because r is just always going to be positive when we refer to it in its kind of like final form. The most simplified form is just going to be positive. In theory, you could have a negative r, and then you just point in the right direction for your theta, and then go in the opposite direction. So, go the other way. Theta can be found from the equation... Oops. Tangent of theta equals y over x. And so naturally, this could be the inverse tangent of y over x is equal to theta. Right, so those are the easiest equations to work with when you're doing polar coordinates and trying to translate from one to the other. If we took some of the functions that we had up above, I don't recommend like doing sine and cosine, but in theory we could. Yeah, not really. Just because, again, here we've got the... Right, if we try to do like y equals cosine x, and then translate that to polar... Right, this is not going to go terribly well. Y is going to be r sine theta. X is going to be r cosine theta. And then we need to solve for r. So I got that backwards, apparently. Interesting. Right. So if we do rectangular to polar with these, we're going to say everywhere you see an x, plug in the polar form. Everywhere you see a y, plug in the polar form. And then likewise, if we're trying to go back to rectangular form, then we need to find all of our r's, plug in the square root, find all of our thetas, plug in this inverse tangent, and then go from there. Try to solve for y. This is going to be difficult, to say the least, because we have an r inside of our cosine function. But basically this is saying that our right, whether we have this here or we try to move it to the other side, we're going to have another cosine that's just in the way. So yeah, this is not going to go well. that particular company sells moonshine out of Manchester. I got this as a gift from our neighbors who left, as you can't ship alcohol back to the States, especially if it's open. All sorts of illegal. And so they were just like, all right, everybody drink. And then when everybody was done drinking that night, they were like, great, now everybody take some home. And then pretty much all the leftovers after that went to me. So this is almost the last of it. Tonight we just had like, yay much in a mason jar. And I was like, why do I want to dirty a glass? Hmm. Anyway. We also have different other shapes that we can get in polar coordinates. So there is, if r is equal to sine of theta, then what actually happens here is kind of an interesting thing. So I would recommend like going through and actually saying, okay, if theta is our independent variable, r is our dependent variable, and we go through all of the basic basic theta values that we typically throw in. You can do this by hand, right? So it's going to be 1/2 root 2 over 2 root 3 over 2, 1. Right, we'd be able to see this. And then okay. When we get out here, we look at this and we say, okay, from theta equals 0, we have a 0 value. When theta is pi over 6, so this is going to be pi over 4, pi over 6, and pi over 3. Pi over 6 is a half. Pi over 4 is going to get us 0.707. That's under 3/4. Pi over 3 is going to get us root 3 over 2, which is 0.86. That's about here. And then pi over 2 is 1. So we're going to be up there. Now, if we connect the dots, with the understanding that as we increase from 0, right, our angular value is going to increase very slightly for our R value increasing quite a lot. So we're going to get this kind of curve that comes out this way, ends up going through a half here, going through these other values here, and then curving around and hitting 1 at pi over 2. Right? So then, when we come down from there, so we go to 2 pi over 3, 3 pi over 4, and 5 pi over 6, and pi, then what happens is we end up going down pretty much the exact same path that we had on the way up. Right? These are symmetric. Comes around, and then eventually it reaches 0 again at theta equals pi. Now when we move into the third quadrant and we get the angular values that are down in the third quadrant, then we look at their sign values. Those are also negative values. So instead of having a value of pi over 6 in the third quadrant, or when we have pi over 6, that's 7 pi over 6. At 7 pi over 6, we have a value of negative 1/2. So rather than having an R of +1, we have an R of -1. Right, so for theta equals 7 pi over 6, right, when theta is 7 pi over 6, we're in the third quadrant, and that has a sign value of 1/2, but then since it's a negative 1/2, then we have to swap the direction, go up in the other direction again. So now, as we go out to 2 pi, this is overlapping the same circle again. This is going twice through the same locations. Alright, we're going to see the same thing for r equals cosine of theta, but now this is going to start with a value of 1 at theta equals 0. So it's going to start out here away from the origin point. And then, as we increase, it's going to start coming up like this. Our theta is increasing in value, so it's going to go around, but then also the r value is decreasing from 1 down to 0 at pi over 2, theta equals pi over 2. So it's going to make the top half of a circle, and then it goes negative, which means that as we're getting stuff in the second quadrant, it's going to start having negative r values and get us stuff down in the fourth quadrant in terms of our picture.
Sometimes creating an ad campaign can feel like you're talking on mute.
Sorry, we can't hear you. Say that again?
But advertising on Spotify can help your business turn up the volume. With our easy-to-use ads manager, you can create new audio ads from scratch or repurpose existing video assets. Then we'll deliver your ad to an engaged audience that is ready to hear and see your message. It's that simple. Learn how Spotify can add more to your mix at ads.spotify.com.
Alright, so 1/2 and 1. And again. Nope, not y. R equals cosine of theta. Again, at a theta of 0, we have a value, r value of 1. At theta equals pi over 6, we have a value of 0.866. At a value of pi over 4, we have 0.707, or root 2 over 2. And then pi over 3, we have a value of 1/2. And then at pi over 2, we have a value of 0. So this is going to make these 5 points. It's going to come up like this, go around like that. Going like that. And then again, as we move into the second quadrant, these values are going to be negative. So here, but r equals -1, meaning we have to throw it back down. It's going to go in the opposite direction, and then we end up here. Because eventually, theta equals 2 pi. We're all the way back out at 1 again. Yep. And with a reminder that since we just did this, this is going to go around twice through all of those same locations. So sine of theta, cosine of theta, they go around twice. And we just end up with circles, but double. Oh. Man. Now the more fun ones happen. And if we've been doing, in my pre-calc class, for example, what do all the function transformations do, right? Students will start looking at this and think, oh, so this is no longer going to just, you know, make it twice as large. Always fun. Right, in this case, it does make it twice as large, but what does it make twice as large? It's not just the y values, right? True, yes. Right, this is not the same as the Yeah, I got you. I should not put that in my mouth right now. Trying to talk, you know? Right, so r equals 2 cosine theta makes the radius twice as large at all points, which still doesn't change anything really, right? It's still going to make a an equivalent shape. It's still a circle, but now the radius is twice as large, so out here we're out at 2. The center of the circle is now at 1. 0 is still at 0. And now when you say, okay, you know, I take the 60-degree or pi over 3 ray that's coming out from the origin at pi over 3, this is going to end up meeting up with the circle at 1. Yes. Boy. No. That's pi over 4. Jeez. That's pi over 4. Right, the horizontal and the vertical are identical to each other. Oy. Yeah, well, don't worry, Zach. I'm with you. Also, not making sense at the moment. Don't worry. Right, so then r is equal to, at this point, at this exact point here, this is now going to be just root 2, because we have a 1 and a 1 as our sides. Or I suppose we could say r at pi over 4, just to be a little bit nicer about it. Okay, but again, the point here is really just we're making the same shape. It's just going to be larger than the previous one. So having a multiplier out front is pretty much the same as when we had Cartesian coordinates. The only difference now is it's not just affecting the y values. It's affecting everything from the center out. So this is not really a like vertical stretch or horizontal stretch. This is a what we call dilation from the origin point. Right? Whereas this and this are not dilations. Right? These are unidirectional stretches. Right? Whereas a dilation goes from a single point out. Unidirectional stretches are going from a line away from that line or toward that line, whichever way it is. Okay, so the much more interesting thing that we could do is say what, man, I keep doing y equals, r equals cosine of 2 theta, or yeah, 2 theta. So in this case, what we're doing is we're saying, okay, now theta is going to report back and if we want, for example, our pi over 6 that we had up top to be plugged into the cosine of theta, or cosine of 2 theta, then pi over 6 as 2 theta is going to mean that theta is going to be pi over 12. And then pi over 6. And then pi over 4 is going to become pi over 8. Oop. Yeah, because that was pi over 3. Right. Pi over 4 becomes pi over 8. Pi over 3 becomes pi over 6. Pi over 2 becomes pi over 4. So now, in order to get the nice values, we're reporting back twice as often. So the cosine at 0 is 1. At pi over 6, the cosine of 2 theta, the cosine value is going to be root 3 over 2. At pi over 4, this is going to be root 2 over 2. At pi over 3, the cosine value is a half, and at pi over 2, the cosine value is 0. Okay, now we increase it again on the other side. So now this is going to be, the next one is usually 2 pi over 3, so now it's just pi over 3. It gets doubled, becomes 2 pi over 3. Right? 3 pi over 4 is going to be 3 pi on 8. um, 3 pi over 4, 5 pi over 6 is now going to be 5 pi over 12. And pi becomes pi over 2. Right, so then this is also going to get the negative values of negative 1/2, negative root 2 over 2, negative root 3 over 2, and negative 1. Okay, now what does this look like? This is going to be... This is super rough, by the way, so... And yes, I know that I could use the circle tool right up there, but this is, you know, it's an exercise. We're trying to make it better. Okay, 0, 1. So we're out here. This is again a half and 1. This is pi over 4. This is pi over 8. This is 3 pi over 8. And then each of these are going to have, like, nice ones that are immediately around it. And they have a gap of unused ones. There's one unused one between each of those triples. Syntax error. I mean... If you know the relationship, then you don't need to memorize it, and it just becomes memorized second nature. You don't have to memorize anything from zero knowledge. So... While we're on ad break, I'll hit my, I'll do my... Well, that doesn't make any sense, does it? Uh-huh. Just like Ramanujan, yeah? Alright, so we go from here. Ads are going to start in like 30 seconds. It's fine. Okay, so we start from here, and we go from 1, 0 in Cartesian. and we do angle here. All right. You go all the way around, right? And that is that theta is going to be 2 pi. When we don't move, theta is going to be that's not what I wanted. Theta is going to be 0. All right. See you in a couple. Add minutes. Add break. Add break. 3 minutes. Add minutes. See you in a few.
The rich think life is so easy.
The man, he showed up.
You can just pay someone to do everything for you.
He cooks, plays with the kids.
But good help is hard to find.
Thought I'd see how the other half lived.
And protecting your family
There's something strange about him.
comes at a deadly price.
Somebody's out to get me. Thank you so much for letting me into your lives.
Malice, starring Jack Whitehall and David Duchovny. New series. Watch now, only on Prime Video.
At Grapetree, you'll find fantastic deals, like our best-selling Supreme Almonds, now for just $8.99 a kilogram, or 3 for £25, or 3 for 2 on our fantastic range of exotic herbs and spices. Plus, use code AUTUMN20.
All right, almost there.
Massive 20% off a £40 or more spend on selected products when you order online, or shop at one of over 180 of our stores nationwide. If you're looking for big deals and good value, Grapetree is the place to go. Grapetree, your health, your products.
Okay. So in terms of trig, we started out by saying that when you want to look at, you know, the overall patterns and everything else that's going on, simplify this by saying that since angles, right, we can scale up or scale down anything we want, make it all into a unit circle. So r is equal to 1, cool, set it up. Then, if we want to, we can say, like, okay, the distance around the circle is going to be representative of the, oh, I hope not. Check, check, check. You're not just picking up like Spotify, right? There does appear to be something at about negative 50 decibels, but you should not be hearing that. No, no, there is the CPU fan, which is just out of arm's reach and under a desk. I guess I got two of them, so. But that is the only stuff that is actually making any noise in here. I also don't have the filters up, I think, because it was too much of a pain in the butt. It was not capturing, like, my voice sometimes. Yeah, that's fine. I can also just turn the music up a bit. I will apologize-ish for the ads that come on Spotify. It's a pain in the rear, but it's the only thing I can do at this point because it's either that or the YouTube ads that come on when I go to YouTube or whatever else. So, I hereby do not... but it's not doing what you want. Oh. It's always the way. Okay. So when we're dealing with angles, we'd said, long time ago that the issue that we have is that degrees are essentially arbitrary. Like Y0 to 360, right? It was basically, it's the Babylonians' fault. They took 60 squared and made all of those individual 3,600 gradations going all the way around the circle, and then they just marked off every 10 as being one unit, 1 degree. So they were able to use 60 squared being their particular base, right? 60 was the base in Babylonian times. Yeah, it's nice, but I let that happen when you're doing, like, compass stuff. So, in order to be non-arbitrary, what we do is we say, okay, let's tie it to the circumference of the unit circle. And then we just scale it up or scale it down depending on how large the radius is. So we know that, for instance, S is equal to R theta in radians is going to get us meaningful values that have to do with the circle itself. It is fundamental properties of the circle. So going from 0 all the way around to 2 pi times r, if r is 1, then we just say the arc length is the angle. So go like this, and we say that this arc length here is theta, and then this arc length here is also going to be theta. Or the angle on the inside is theta, and the arc length on the outside is theta. Okay. So then we mark out easy angles. So halfway around is going to be pi. Easy enough. Half of that is going to be pi over 2. Halfway between the bottom two is going to be 3 pi over 2. And in fact, it would be easier to count this. So this is going to go from 0 to 1 unit pi over 2. 2 units of pi over 2 is pi. 3 units of pi over 2. 4 units of pi over 2 is 2 pi. Okay, and then cut it again. So this time we'll go, roughly speaking, halfway through pi over 2. The arc is now going to be pi over 4. And that's another unit. 1 pi over 4 is there. 2 pi's on 4 is here. Pi over 2. 3 pi's on 4 is going to be here. Four pi's on 4 is pi. 5 pi's on 4 gets us down here. 6 pi's on 4 gets us to 3 pi over 2. 7 pi's on 4 gets us over here. And 8 pi's on 4 gets us back to 2 pi. The area enclosed also pi over 2, or theta over 2. Well, it's pi r squared, right? So theta over 2 seems right. Yes, because pi over 4 is going to be an eighth of the circle. Yeah. But only because the radius is 1. So, ends up working out nicely. Okay, then when we go like this, shoot. It's the best place to do it, really. Hey, what do you know? It's close enough. Yeah, it's not quite. That's better. Alright, so for these, these are now going to split the circle up into 6 for the ones that are up, which then makes it pi on 3. So 1 pi on 3, 2 pi on 3, 3 pi on 3 is back to pi, 4 pi on 3 is down here, 5 pi on 3 is here, and 6 pi on 3 is back to 2 pi. We split that in half again, and now this is pi on 6. 1 pi on 6, 2 pi on 6, 3 pi on 6, 4 pi on 6, 5 pi on 6. It's Penn Center. Hello, everybody. Good evening and welcome. My name is Obi-Wan Pez. This is N-Simplex Pachinko, and right now we're talking about the unit circle in order to kind of leverage, make sure that everybody knows how it works. And then we're also working on polar function graphing over on the other side. Oh, it's me. Right, exactly, Cosmolano. Good evening, Penn. Hope everything went well with stream. So yeah, we're using the pi on 6 unit. There it is.
I have a pen. I have an apple. Apple pen.
Good evening and welcome, everybody. Formally, now that you're all here. My name is Obi-Wan Pez. This is N-Simplex Pachinko. We're talking about the unit circle, and yes, exactly what several people have just said. I never remember this thing. Perfect. So, we're splitting up the circle into its constituent parts based on the arc length that we're given. And again, the reason is that the angle on the inside here is the same as the arc length when r is equal to 1. Makes it nice and easy. This also makes a non-arbitrary angle value, whereas the Babylonian system of using 360 degrees for one circle is arbitrary in the sense that it was based on their number system. But once you divorce yourself from that number system, why 360? A lot of students would be like, oh, I don't know, it's a nice number. It's what you put on compasses. They missed the point. Okay, so what we did was we split this up one bit at a time, and then we look at each of these things and say, okay, this is a unit. So this is 1 pi on 6. 2 pi's on 6 ends up being pi on 3. 3 pi's on 6 ends up being pi over 2. 4 pi's on 6 ends up being 2 pi over 3. Then 5 pi's on 6 is new, so we have to write that down. 6 pi's on 6 is pi. 7 pi on 6 is going to be down here. 8 pi on 6 is going to be 4 pi on 3. 9 pi on 6 is going to be 3 pi over 2. 10 pi on 6 is going to be 5 pi over 3. 11 pi over 6 is going to be the last one here that's empty. And 12 pi's on 6 is going to be 2 pi again. So we're back around that way to 2 pi. Okay, now we also have pi on 12, which is halfway between our pi on 6 values. However, we tend not to use it. Or at least, we tend not to make the students use it all that much because it doesn't have a nice value that we're going to be able to work with. Whereas pi on 6, pi on 4, pi on 3, and pi on 2 and pi all have nice values that we can play with. Okay, now, how do you get the coordinate values of all these locations? Give you a hint. You don't need to do all of them. You don't need to memorize the unit circle. You don't need to memorize pretty much anything in trig. Once you understand how it's constructed, and if you've done it, if you've practiced it a few times, you've looked at it a few times, you will instantaneously recognize all this stuff without the need to sit and memorize. You will have memorized it through practice rather than memorizing it through mnemonics or whatever bullshit sort of stuff you've been doing. Sorry. But it's true. Okay, so how do we get the coordinates for this stuff? Well, the easy ones are all of the full and half pi's, right? Super easy. We have a radius of 1, and those are orthogonal to each other. So the origin is 0, 0. So if we go straight to the right, that's 1, 0. If we go straight to the left, that's negative 1, 0. If we go straight up, that's 0, 1. If we go straight down, that's 0, negative 1. Okay, less easy. How do we get the pi's on 4? All right, let's start with that one first. Well, if you look at it, we take this pi on 4 location and we drop an altitude straight down to the x-axis. It makes a right angle with the x-axis. What do we know about this? Well, we totally don't know what the x and y values are, right? If we're developing this from basic principles, we don't know what the x and y values are, but we do know what the radius is, right? The radius is always 1. So with the radius being 1, coming from the origin and going out to here with an angle of pi over 4 and a right angle here, what's that one? Right? Or what's that one? Right? We know that this is also pi over 4, or 45 degrees if you want to use degrees. I tend to use degrees when I'm talking about internal angles of triangles and that sort of stuff. Not exactly fair, I know. A right angle is pi over 2. 2 pi over 4s makes another pi over 2. 2 pi over 2s makes pi. That's 180 degrees. That's it. That's all a triangle can sustain. So now we have two equal angles. What does that mean? Well, that means that the opposite sides that are subtended by those angles have to be the same. This is the x value. This is the y value for this particular point that we want to get. Well, if the angles subtend equal side lengths, then that means that y equals x and x equals y. Makes it kind of nice and easy. Let's just let it be x for now. That means that we have a Pythagorean identity here of x squared plus, again, let's go basic, plus y squared equals 1 is true for anywhere on the unit circle. Right? Anywhere on that unit circle, that is true. In this particular case, we know that x squared plus x squared is equal to 1. Which means that 2x squared is equal to 1, which means that x squared is equal to 1/2, which means that x, well, the absolute value of x is the square root of 1/2, which is 1 over root 2, which is root 2 over 2. However you want to know what that value is, right, doesn't bother me if you're my student. Some teachers want you to know the rationalized denominator version. I don't care. It does make a nice little pattern when we're done, but that's not the point. Okay, this says that the absolute value of x is equal to root 2 over 2. Which means that anywhere that we have an x and a y value that are of equal length, regardless what direction they're in, the x and the y values will be root 2 over 2, or 1 over root 2. The only thing that determines whether it's positive or negative is which one you're talking about and which quadrant you're talking about. And that's super easy. So over here, right, 3 pi on 4, this is saying that we're going to have we're going this way, so that's a negative x, so negative root 2 over 2, and we're going this way, which is up, so that's positive root 2 over 2 for the y direction, right? Pi on 4 over there is going to be a positive root 2 over 2, because we're going that way, and up, so positive root 2 over 2 as well. Third quadrant, we're going to the left, which is a negative x value, and we're going down, which is a negative y value. Don't memorize this stuff. Know, right? Think it through and tell me what direction these things are in, and therefore, is it positive or negative? You know that. That's basic Algebra 1 stuff. Right? So that's how you get pi on 4. Works out pretty nicely. So, pi on 4 is going to be what's called, in this case, the reference angle, meaning that if you need to know what 5 pi on 4 is, you need to remember to yourself, this is the same angle as pi on 4. But it's just in the third quadrant, so my x's are negative and my y's are negative. Hey, PhD Lingo. Noise. Right? Make an angle with the x-axis. That's your internal angle, or the reference angle that you're going to be using for wherever you are in the circle. So again, pi on 4 in quadrant 3. And that gets you your understanding of what needs to be positive, what needs to be negative. Okay, now, how do we get pi on 6 and pi on 3? Slightly harder, but honestly, not too bad. So we go like this. We say we're going to take our unit circle as it was, rough sketch. Not that rough. Oh, God. We're going to take our rough sketch here. And we're going to mirror this both up and down. Yeah, this is totally not going to work. Oh, God. Whoa. So gross. Marginally better. Might have to start listening to lectures when we're offline. Yeah, go watch... I mean, you could always go watch a boring professor. Okay, what have I just made? This is pi on 6. Also known as 30 degrees, if you want to translate that back into degree measurements. Ed Copeland. Nice. This, right? This, if we go down, is a negative pi on 6 or a negative 30 degrees. If we go from negative 30 degrees to positive 30 degrees, we've just gone through a 60-degree arc. And we know that the radii of this thing have to be equal to each other. So this is a radius of 1, this is a radius of 1. That means that this angle here has to be equal to that angle there. And then what's the third angle, right? We just said, well, it's 60 degrees. So cut 60 degrees out of 180, we're left with 120. Cut that in half for the other two angles. Hey, would you look at that? They're also 60. So we just made an equilateral triangle. Right? All of this stuff here is the same angle as the other two. So what does that mean for us? Well, that means that the whole length from here to here vertically is going to be 1. Therefore, each of those separate pieces is going to be a half. And we already know that the radii are 1. So again, Pythagorean identity, because these are right angles. We now have x squared plus y squared equals 1. Well, we know that the y is a half. So what's x? Right, x squared plus a half squared is a quarter. So x squared is going to be equal to 3/4. Which means that the absolute value of x is going to be equal to root 3 on 2. Now I will say that the y value could be plus or minus, but it doesn't matter at all because it's being squared. So, whatever. This means that the absolute value of y is equal to 1/2, and, or when, the absolute value of x is equal to root 3 on 2. And again, look at what quadrant you're in. And look at the orientation. Because, right? We've got a 60-degree angle in here. That's pi on 3. And this other one, the smaller one there, is pi on 6. So pi on 6, pi on 3, flip it around. Pi on 3 can be your central angle, and pi on 6 can be the one that's floating off in space, the complementary angle. Yeah, I mean, like, You would hope so, given that I've taught this for 15 years. But I don't know, like, I get really frustrated sometimes, because, like, teachers are like, oh, I'll just teach it however I usually been teaching it. And it's just like, well, that doesn't work. You know it doesn't work. Right? So pi on 6, again, this is the long side is your x. So the long side was root 3 on 2. The short side was a half. For pi on 3, the short side is your x. So that's a half. The long side is your vertical. That's root 3 on 2. Yep. Yeah, so the other thing is that people don't know this derivation, and it's super easy. Because all you need to do is double that triangle from just being up here to include the lower half. You know, mirror it. Mirror it. Mirror it. And then now you've got the exact shape that you need for an equilateral triangle. And then now, again, your x's and your y's have those values for pi on 6, and then they're reversed for pi on 3. So again, you want to know what you have here? Okay, 2 pi on 3 is going to be a short negative, because we're going to the left, but a tall positive, because we're going up, root 3 on 2. Okay, what is one we haven't done? 11 pi on 6. Well, this is a long x value in the right, in the positive direction. So root 3 on 2, comma, and we're going down a short distance, negative 1/2. And the other thing is, right, do you remember which one is longer and which one is shorter? The square root of 3 is bigger than 1 because it's bigger than the square root of 1. Square root of 3 is bigger than the square root of 1. Thank you for the follow. Okay. So then what about pi over 12? Well, you've got to find some trig identities to make that work. So we'll skip that for now. However, now that you've got all of this stuff for the unit circle, how do you figure out the trig functions? Right? So the logical next step here, how do we figure out the trig functions? Well, turns out there's actually a nice way to do this too. And yeah, it's not super simple, but it's pretty reasonable, and most people like it. There are two ways that I do this. One is I will draw random angle, right? R is equal to 1. When R is equal to 1, right, the sine function is a vertical distance ratio. Okay? When you start from 0 and then start moving up, we're starting from a 0 value on the sine function because it's the vertical one. Knowing the names is helpful for communication, but knowing the concept is much more important. So here, we start from a 0 vertical value, and then as we go up, as we start creaking our way upward, this vertical distance becomes larger and larger. And on the unit circle, right, the sine value is the vertical distance. It just is the vertical distance. Because we did this earlier, sine of theta is equal to y vertical over r. You're comparing the two if you already know SOHCAHTOA stuff, right? Your sine has the ratio of the opposite over the hypotenuse. Well, same deal here, right? It's the vertical distance compared to your radius. Vertical distance compared to radius. So what is the ratio of those two things? Well, there you go. Y over r. In this case, when r is 1, sine is the vertical distance. Similar. The cosine is going to be the horizontal. Or, because cosine of theta is equal to x over r, again, you're looking at this as x over r. R is 1. Cosine of theta is x on the unit circle. So it just is the horizontal component, right? And then what you do is you either scale it up or scale it down. If your r is bigger, then your cosine is going to be, or well, the x value will be bigger. But the cosine ratio will stay the same because you're scaling up both your x and your r at the same rate. Right? We're looking at similar triangles here. So if we made a different circle that was only this big, right? We'd have this thing, but then our radius would only be that thing. So again, similar triangles scale proportionally. Okay. So then, here's another cool thing that you definitely never learned. Most of you. If we were to draw the horizontal component here instead of along the x-axis, the central angle is this angle here. We also know that this is going to be parallel to that. And our line here is a transversal. Therefore, theta here is going to be the same as the opposite interior angle here. This is also theta. Wait for it. Okay, this means that this other angle, let's call it alpha, is also going to be opposite interior angles of this angle here, alpha. Now, what is the sine of alpha?
Nothing beats family time. Quality time spent with catching up on your debt. Business admin cutting into family time. Sounds like you need to supercharge your bookkeeping with Xero. With automated bank feeds, smart reconciliation, and online payments.
Almost, yep. You got it. Yep, pi over 2 minus theta. Yep. So alpha is pi over 2 minus theta, and likewise you could swap them. Theta is pi over 2 minus alpha. So up to you which way you want to go. But this means that sine of alpha, if you look at the diagram, the sine of alpha is x over r. The cosine function is the sine of the complementary angle. So you may have heard that before, but you definitely didn't see it in this particular arrangement, right? Drawing this horizontal from this point here, right? You can either think of it as the complementary angle being up here above theta, or just in the opposite corner, in the opposite angle in the triangle. Either way, right? So this also means that the cosine of alpha is going to be equal to y over r. And either way we go with this, right, this means that the sine of alpha is going to be equal to the cosine of... hang on. Is equal to the sine of pi over 2 minus theta, which is also equal to the cosine of theta. So the cosine of theta is equal to sine of pi over 2 minus theta. So if we relate theta to theta, right, we get rid of the dummy variable, our alpha angle. It's a dummy angle. We're not using it for real. It's just a placeholder or an extra thing we're using for a minute. Okay, fair enough. So, there are multiple ways that I like to do the next bit. I want that one, I want that one, and I want that one. Oops. I don't really want the rest of the stuff. No. Okay. Now. Same angle, give or take. I don't know what it is. Okay. Okay, now, nope. Deselect. Give me another one, this color. What's this? Right, this one's a tangent line. It's vertically connected to where we started from. So, you know, our theta equals 0. As we move up, right, this point that the terminal side of our angle is going to hit that tangent line is going to then keep moving up and up and up and up and up. There's something interesting that happens when you consider what happens when we have our y here, our x here, right, in blue. And then when we look at what happens when we scale this up. Yes. So when we start looking at similarity, we now have something that's rather interesting, right? We have two different radii. One in blue, one in orange. Now, if I want to compare, for example, this length here. Right? Let's call it T for using the tangent line. If I want to compare T to 1, right? This is the vertical compared to the horizontal. And now I use the similar triangle that it's attached to. The side lengths have to have the same ratio So it's going to be vertical to horizontal, y to x. Some of you are going to be screaming at the screen right about now. Additionally, and rather interestingly, if we take all of the individual values that we go around the circle with, you know, this t of theta as a function of theta, what this turns out to be is, oh, would you look at that, compared to the angle theta, this is the opposite over the adjacent. This is the tangent of theta. And this means that the length on the unit circle, the length of that line on the tangent, the length of the tangent line is going to be the value of the function, tangent of theta. You take the tangent line either on either side of the circle, it doesn't really matter, and measure that distance. Right? You're always going to end up with the distance. And in fact, if you were to take the opposite angle here, if you were to take the opposite angle, and then draw in the terminal side as a line, look where it's connecting, right? It's in the positive region. It's in the positive region of the tangent line attached over at 1, 0. So you know, we don't even need the or statement here. And similarly, right? If you have another line on this side, where's it going to? Either the second or the fourth quadrant. That angle has a position on the tangent line in the negative direction. And if you want to know something even cooler than that, this is connected to 2 points. XY and 0, 0. Where have you seen that formula before? Right? So the tangent of theta, the distance that you travel along that tangent line, is going to be identical to the slope of the terminal side of that angle. Again, on the unit circle. If it's a bigger or smaller unit circle, or than the unit circle, bigger or smaller circle than the unit circle, then you similarly have to scale your value. But it's the same thing. So you do y over x, you're connected through 0, 0 for your terminal side, the slope of the terminal side is your tangent value. All these cross connections are wild, by the way. You want to know something else that's wild? Right? This isn't the only way to do it. You could have taken your tangent line and made it at wherever your endpoint is, wherever the terminal side is. Okay, now I'll come back to that in a minute. If we look at this, a tangent and a radius on a circle always make right angles to each other. This is a radius, so it has a distance of 1. Hey, guess what? This is also t. That distance is also t. Because, and you can prove it, right? That's a right angle. This is going to be theta. So what does that mean? This one over here is going to be alpha, right? It's going to be the same angle as is over here. Has to be. Two of your angles are the same. And you now have a radius for both of these. Oops, I got the wrong one, but you get the idea. It's that one. Right, the big triangle. And since the radii are both 1, right, that is now angle, angle, side. So with angle, angle, side, those two triangles are congruent to each other. And so therefore, therefore you can say, yes, this is also t, as is the other one over there. Also, if we want to take this distance, the distance from the origin out to the tangent line as a straight line, we can call that S. We can run the same thing. We can compare S to 1 just as much as we can compare, again, S to 1, big to short, as much as we can compare big 1 to short X. Right? So we compare here 1 to X, long to short. Oh, I guess technically this is S over R, but yeah. We'll leave it like this for now. Again, unit circle. What does that mean? Well, that means that S is just equal to 1 over X. And again, if we were doing this as I mean, technically, but I wasn't too worried about the colors in the equations. But if you want, you could also compare the S diagonal to the 1 underneath. Right? That's the hypotenuse to horizontal. And then the hypotenuse of the short one is 1. And the hypotenuse of the short one is X. So those ones are interchangeable with each other, however you want to do it. I guess technically, like, this is RS over R, and then this is R over X on the other side. I don't worry too much about it, because this all just goes out eventually. The idea is that if you want to have one that is then scaled appropriately, your S as a function of theta is going to be equal to R over X, which is 1 over X over R, which is 1 over cosine of theta. You've heard of that one before, I'm sure. That's your secant of theta, which, if you caught my meaning on it, the S is a thing that goes from the, like, through the origin and through the outside of the circle, or through the circle twice if it's a line. So any line that goes through a circle in two places is called a secant. This is just a special secant that aligns with the angle that we want to deal with. It's the secant of this angle. So the secant of theta is going to be that ratio of, oh, whoops, I got that backward, R over X. And now we did that with this triangle as well. Doesn't matter which one you're using in all of this. It's all the same stuff, right? If you wanted to use the other triangle over on the side there, you'd be dropping an altitude here for your X and Y, which makes it a little bit harder to see the similarity, but as soon as you kind of reorient it in your mind and be like, okay, well, these angles are the same.
Shame. Shame. Shame.
Thank you, Famished. Gotta scare me every so often, right? And if anybody's interested, I put subs on discount for the next 24 hours. You can do that offline, you can do it online, whatever you feel like. I'm going to be putting up some... I'm going to be putting up some alerts, both for free, you know, exclamation lurk and unlurk will eventually have some sort of sound effect to it. And I'll make a command list, basically. And then once I import all that stuff, you'll be able to have a lot of fun with it, I'm sure. A bunch of them are coming from Square One TV, my favorite math show from the 1980s and 90s. And if anybody doesn't know what Square One TV is, it's worth it. It's worth a look. I don't have any connected here, by the way. This is just my YouTube channel. Both of them. Gaming content is at Obi-Wan Pez, and math content is at nsimplexpachinko6542. I gotta see if I can rebrand that. I tried at one point and it was like, no. But I might be able to. Okay. And then there's another set, which, by the way, you could see right here, again, in this secondary triangle, because that secondary triangle is now here, with a side length of 1, and now a secant, but the secant of alpha, and the tangent, but the tangent of alpha. So, we'll be back. 3 minutes. Go cycle that water. Go get something to drink. Go get a snack, whatever. And we'll be back here in 3 minutes. Thanks, everybody.
Amazon Black Friday week deals up to 40% off. Get the perfect gift for your father-in-law, the Deal Hunter. If only he knew about the deal you got on his gift, he would embrace you, just like he does deals. Oh, I guess we're hugging now. Well, that's a long hug. Oh, it's still going. Oh, it's a Black Friday week hug. It's a deal hug. Up to 40% off this Amazon Black Friday week. Ends 1st of December.
At Grapetree, you'll find fantastic deals, like our best-selling Supreme Almonds, now for just $8.99 a kilogram, or 3 for £25, or 3 for 2 on our fantastic range of exotic herbs and spices. Plus, use code AUTUMN20 for a massive 20% off a £40 or more spend on selected products when you order online, or shop at one of over 180 of our stores nationwide. If you're looking for big bags and big value, Grapetree is the place to go. Grapetree, your health, our products.
I look at people and I wonder all day, who are you and you are not the one in your way? And then I think about myself and I stayed. I'm a pretty boss, look almost your brain waste. I'm a freak in the sheets, but I got class. I'ma grab an ass if you want it. Best you ever had, give it to you bad. Ooh. I'm the girl that they don't talk about, quiet with a big mouth. Listen for the doubt, then call it. Make you out for what you say to me. Look at every single date. If you got what I need, then I'll take you on like a big deal. Legs you can unfeel, key in ignition. Just keep me full like I had a meal once in a while.
Was ist das Top Dog Law? Das that we hoist. Alright, so typically we do a quick bit of lifting, 20-pound weights, and go until I get bored or hit failure. Usually just curls till we get close, and then start pulling. Just do some like underarm lifts. I don't know what you call them. Sorry. Bonk. All you out there get some sort of workout equipment. Go do some push-ups, what have you. Lift a heavy object and put it down again. Yeah, we're getting there. Alright. lift up. Our daughter got one of those exercise bikes because she had, like, she was developing weird nervous tics during COVID. Yeah, standing desk also helps. So yeah, she was developing some weird nervous tics during COVID. And apparently, like, preteen girls during COVID developed tics at like this weird alarming rate, and they're like, what is going on? So it's just like this energy that they're unable to put anywhere else, and it was just, for some reason, preteen girls at a much higher incidence rate than anybody else in the entire population. Bonk. Good times. I was telling Famished earlier, I unfortunately lost part of my tooth today. So I'm going in on Friday to get the rest of it yanked out, because it's a mess. Good news, also somewhat bad news, it doesn't hurt. So that means that it did bad things. It did such bad things that that nerve is like gone. So they'll probably put some Novocaine on it and then just be like, yep, that was easy. Right. So we have here the tangent and the secant, but this time it's of the alpha, the complementary angle. So what we want then is the complementary tangent and the complementary secant. You have words for those. Right? And again, if we dot this over, we have our x here, we have our y here, and we have our 1 up here. That's a right angle, and that's theta. So therefore, right, or that's the reference angle of theta, but whatever, we can call it all the same good stuff. Which also means that this one way out here is also theta. Right. So here our t compared to 1 is the long leg compared to the short leg. So long leg compared to short leg, t of alpha is going to be equal to, that's x over y. So we can call this the cotangent of theta is going to get us the same thing. And we shortcut it with cotangent COT. Okay, and then the secant, but of alpha, is again going to compare this to 1, right? So this is hypotenuse compared to short leg. So hypotenuse is 1 compared to short leg is y. So S of alpha is going to be equal to short over, oh no, sorry. S over 1, yeah, is equal to 1 over, that's not right. Yeah, hypotenuse over short leg. It's 1 over y. So then this is the cosecant of theta, which is 1 over y, which is 1 over sine of theta. And the cotangent of theta is 1 over the tangent of theta. Why am I on minicam? Math night. Zooms it in a bit extra, so a little bit easier to see. Not much. Right? So now we have all the trig formulas and all the relationships. And really the thing that you want to like remember from all of this is just a matter of like, how do all of these bits connect? Well, make a triangle that's going to expand out until it hits whatever relationship it is that you actually need. If we wanted to do it in the old style, we would do the co-function stuff on this one. Right? So here, this would be the cotangent of theta, right along there. And out to here from the origin is going to be the cosecant of theta. Until it gets out toward the cotangent, or until it actually connects with the cotangent, and then a 1 here for our radius. So I've got like a couple of pictures somewhere that show what it is that you actually end up, or it's a picture that shows all 6 of the relationships in one photo. It's pretty amazing, it's pretty wonderful, and students were like, okay, it works. It helps me remember, I guess. But yeah, that's the basic idea, is that if we were to draw this in, what would be like the easiest way to, wait, yeah. Right, if I want to represent this all in one, maybe a little crazy, but it's alright. Then what I've got is, with this being 1, right, or r equals 1, I would call this length here the sine of theta, with this angle being theta. I would call this length here the cosine of theta. I will call this length here the tangent of theta. And that one would be the secant theta. Nope. Don't do that. Right, cotangent theta, and cosecant theta. Wait, no, that's not the cotangent. Jeez. Oi. That's the cotangent. There we go. It's like, that doesn't make a triangle. Yeah, the fun part about that is the tangent and cotangent make a square of side length 1. So because it's the radius. Right, we have our radius here. We have our radius here. R equals 1, R equals 1. So, this is your like single picture of all trig functions. If you can remember that, it's an option. My big thing, again, is that I would recommend that you remember how all of this stuff is made, and that makes it much easier to figure out. And this also gives you the information you need in order to see that, okay, if we take the small triangle, sorry, you can't see that. If we take the small triangle here, right, sine squared plus cosine squared is going to be equal to 1 squared. Hey, look, there's another Pythagorean theorem right here, right? The 1 squared from this one plus tangent squared going up like this is equal to secant squared diagonal. And also 1 squared here going up plus cotangent squared going across is equal to cosecant squared going diagonally. Slightly misleading if you read it wrong. Let's flip that around, actually. So, tangent squared theta plus 1 equals secant squared theta. And also, right, 1 plus cotangent squared theta is equal to cosecant squared theta. Right, now we've got Pythagorean identities. And if you wanted to double check that, you could say, okay, I know that sine over cosine is tangent. So sine squared divided by cosine squared is going to be tangent squared. So if we divide everything by cosine squared on the top row, we get sine squared over cosine squared, that's tangent squared, plus cosine squared over cosine squared is 1, equals 1 over cosine squared is secant squared. Right, we showed that earlier. And then again, if we wanted to go the other way, we start with the top, sine squared plus cosine squared equals 1, and we divide everything by sine squared instead. Sine squared over sine squared is 1. Cosine squared over sine squared is cotangent squared. And 1 over sine squared is cosecant squared. So we verify all of these identities by doing all this. We verify the identities by looking at the pictures that we can make based on all this stuff. And yeah, you might forget what the individual things are called. That's okay. You'll figure it out. Right? But the concepts are the important things. So we're making Pythagorean triangles. We're then trying to expand out all of these individual Pythagorean triangles in order to find relationships that exist between the angle, theta, the radius, 1 in this case, and all of these individual lines which connect all these bits. And again, if we wanted to do it ever so slightly differently, we... Ooh. There we go. That's not what I wanted. Why doesn't this thing read my mind? I mean, come on. How hard can it be? Alright, so we start from 0, we go out like that, give or take. Cool, close enough. Sure. And then we take the tangent. Tangent line. Like that. And then we're going to go up. Right angles here and here. And then if we take this going down here and this going across here, all right, that's also a right triangle. Here is your sine of theta. Here is your cosine of theta. Again, presuming that the radius is 1. That is what those are. And then the tangent of theta is here. The cotangent of theta is here. The cosecant of theta is here. And the secant is here. So use either one of those if you want, a visual model for it. I think this one's a bit cleaner. Most of the triangles are kind of out of the way of each other, just because they're not overlapping, except our blue triangle there. It could work. if anyone's interested in this sort of stuff, I am trying to like get together a more like pre-calculus oriented class. So if you are interested in that, let me know. And once we get like an actual class size, we'll class size of interest, then we'll figure out something. Okay, so r equals cosine of 2 theta. We got these different values for our thetas, which were very strange. So when I plotted them, here's what happened like 2 ad breaks ago. We started with the same 0, 1, or 1, 0 in this case. Our radius is 1 when theta is 0. Cool. We're here. Okay, then instead of being pi over 6 and root 3 over 2, our angle gets doubled before it goes into the cosine function, which means that this is a angular compression. So right, the b in this case is not going to be a unidirectional stretch anymore in the case of r equals a function b of theta minus c plus d. A, so it was a radial dilation. B is an angular compression. So what does that mean in this context? That means that all of our angles now have to be smaller amounts to get to the same area, or to get to the same location that these old angles were from the parent function, from just, r equals cosine theta. So we've taken all of our angles and they're effectively halved. So pi over 12 is now root 3 over 2. Pi over 8 is now root 2 over 2. Pi over 6 is now 1/2. So that's these points here leading up to pi over 4, 0. Well, 0, pi over 4. We won't go there exactly, but... So it looks something like this. Then, pi over 3, which normally is, this big one up here... no, not in this case. It's the small one in here. This pi on 3 normally has a value, or in this case has a value of -1/2. So what that means is we need to flip this through the origin, and we get this point here. 3 pi on 8 is the big spur here, is negative root 2 over 2, so we find like root 2 over 2, and then that should go the opposite direction. There. 5 pi on 12 is going to be this little spur here. Gets us a negative root 3 over 2. Root 3 over 2 is like way out here, 0.866. And that's going to be mirrored through here, down to this area. And then pi on 2 is normally straight up, but now it's a -1, so it's going to go straight down. And now, this is where we get something rather interesting. Now we've got like 2 bits of this. I mean, this sort of looks a little bit like our circle, but now it's like over there instead of being in one specific place with a circle. Okay, the fun bit is what happens next, because this is going to go out like this, and then back around. The next pi over 2 bit going to go to here. So this gets us from pi over 2 to pi. It's the same shape, it's just mirrored so that now they're touching each other. Then, from pi to 3 pi on 2, this is going to go down here, through here, and up to this one. And then from 3 pi on 2 to 2 pi, it's going to go from here there we go. This is what cosine of 2 pi is going to look like. When you take that angular compression and you increase its value, now we're going to get to more places within one cycle of going around and getting all of the angles represented from 0 to 2 pi. So if we assume that we're always going to go from 0 to 2 pi, this is the sort of behavior we get. Right? If we do the same thing with r equals 5 theta, or r equals 6 theta, or 7 theta, or 8 theta, we're going to actually oscillate between two different behaviors. Okay? So the first is here, cosine of 2 theta. When we looked at the circle, just cosine of theta, then we were going over the same pattern twice, and it had one shape to it. It was a circle. That was it. Here, however, cosine of 2 theta, we now have 4 petals to this flower. Oftentimes these shapes are called roses or rosettes. Kind of makes sense. So with these rosettes, with this shape here, we're going to get 4 petals for having a B value of 2. That's a pretty nice pattern. Now, interesting things happen when you start changing your B value to be not just whole numbers. It's also interesting when you just change with whole numbers, but nonetheless. All right, if we were to let r equal cosine of 3 theta, then we've got 0. Pi on 6 becomes pi on 18. Pi on 4 becomes pi on 12. Pi on 3 becomes pi on 9. Pi on 2 becomes pi on 6. Okay, with values still 1, root 3 over 2, root 2 over 2, 1/2, 0. It's the exact same stuff. However, this time when we do it, right, this is going to be 0, 1, pi over 18, pi over 12, pi over 9, pi over 6. Okay, so we're still within this distance here. So if we want to again go from here, get the second quadrant worth of data, 2 pi on 3 becomes 2 pi on 9. Which is going to be a negative 1/2. 3 pi on 4 is now pi on 4. Five pi on 6 becomes 5 pi on 18. And now pi becomes pi on 3. So before we ever get to pi on 3, we've already swept through all this other stuff here. So something like that. Okay, then this is going to sweep through again. Oops. Before we get to pi over 2. No. Nope. Pi over 2 is not. Right. That would be 3 pi over 2, where we would get a 0. So yes, it is before. It's before we get back to pi over 2. Right? Be like that. Then this would end up curving down like this. Back through here. Yes. Okay. And it would end up curving back through and end. But it would go through twice before we reach 2 pi. End petals overlapped, whereas here we had 2 end petals separated. Right, so this is going to be 2 circuits overlapped. These are the skills you can gain as a math professor. There's all sorts of really cool stuff that you can do. If you work with C at all, so inside you got theta minus C or theta plus C. This is an angular displacement. Some people might call it a phase shift even. But basically this is going to start taking your whole picture and just rotating it, changing your starting point, and therefore it's going to change how, how things get plugged into the function itself. D is going to be a radial displacement, which is bonkers. Alright, reason being. Do I not have a Desmos open? That's weird. Alright. Calculator. Nope. Right, so switch to polar mode. And what we can do is say, like, okay, R of theta equals. Thank you for the follow. Hope you're having a good evening. My name's Obi-Wan Pez. This is In Simplex Pachinko. We do math on Mondays and Wednesdays, typically math education type stuff, so discussing how to teach, why to teach. No, how to teach and like different methods and things like that. We're going to do on Mondays, and on Wednesdays we're doing mostly calculation type stuff. We may decide to do more or less than what I've just said, based on how things go. Also, we're usually here for gaming on Sunday, Tuesday, and Friday for all of those individual types of games. So we've got a few different things going on at the moment. Tuesday nights are Nine Souls, which is a totally cozy Tai Chi kitty game. A times f of nope, b times theta minus c plus d. Add a slider for A, B, C, and D. Leave A and B at 1, and C and D at 0. Alright, and then... Okay. Then we said we wanted R of theta is going to be equal to, oh no, F. Cosine of theta. That is not nice. I don't think this is gonna... Wait, what? Okay, whatever. Sure, P. It works. So here we have a cosine function. If we increase our A value, it is going to get large. Again, if it goes negative, it's going to reach out to negative 10. Go to that side. Okay. If we change B, might be a little fast, I suppose. So what we're seeing is that as this increases, the frequency of our particular cosine function also increases. So until we get to a whole number, we're going to have these like values that end up overlapping, and sometimes you do get one that doesn't actually repeat within an appropriate amount of time, and so like this one way down at 0 point something. Okay, that's interesting. Ah, there, you can see it. The tip here is free, so the function didn't come back around and close the loop on this one. Anyway, this is all made with just changing the frequency at which our data is taken. And changing C, we already said, rotates it. Okay. And then our D value is like I said, a radial displacement. So yeah, pretty much. So if we increase D, then what's happening here is now our maxima are reaching real close to 3. You know what? Hang on. Just do 1. And D equals 4. D equals 1. Oh, yeah. Okay, so let's go for a half. What we see is that our large petals here are reaching out to 1.5, and the small petals are only reaching to 0.5. When D was 0, all of them reached out to 1. If we get this to be large enough, i.e. bigger than 1, then actually what we see is we're not able to get back to the origin because our A value is too small, right? It doesn't make enough of the amplitude on the cosine function isn't big enough to overcome D, which this additive amount is just going to get the whole thing to kind of soften its edges. So this is also one way that you could actually make a make an approximation of a square, for example. Right? If we just keep increasing right? Eventually what we see here is this is all rounded out. It still overshoots and undershoots the it still overshoots and undershoots like making a perfect circle. In this case by 3. So we see 103 here and here and here and here. And then we see 97 here and here, here and here. So, makes it interesting. Anybody have any questions on this stuff before we, I think, probably head out for the night, because it is 2 o'clock. You think you made yours wrong? Oh no. D just isn't high enough, yeah. So you do have to go in and poke around a bit, but... Alright. Let's see if we can go raid. Awesome. So we're going to go see Rhaekodactylus, who is one of our streaming friends who does a lot of work with conspiracy theories and trying to like study how conspiracy theories get started, how populations could potentially inoculate themselves against certain conspiracy theories, and all sorts of other good stuff. We'll be back on this channel on Friday, provided I'm not too drugged up from having a tooth yanked. Shouldn't be. Or if I'm not feeling like it, I'll just not. Other than that, yeah, that should be Against the Storm. And then on Sunday, we'll do some Satisfactory, probably, unless my D&D game, or not D&D, just absolutely drains me. But we'll see how things go. Hope you all are having an awesome night, day, rest of your time, whatever. And we'll see you next time. We'll see you in other people's channels, too. So, thanks everybody for coming. My name is Obi-Wan Pez. This is N Simplex Pachinko. Catch you next time.